Hello, and welcome to my Lab 3 video presentation. The purpose of this lab was to determine the distance dependence of the magnetic field of a bar magnet and develop a computational model to describe the magnetic field on-axis, off-axis, and at a 45-degree angle to the magnetic dipole. This report will start off with an introduction, followed by a statement of my major assumptions and the physics concepts used. Next, I will walk through the experimental procedure for the lab and the results I found. Then I will briefly look at the data I collected during the experiment, followed by an overview of my computational model. Lastly, there will be a conclusion and discussion of the follow-up questions. The only major assumption I needed to make for this lab was that all other magnetic fields present in the testing area, other than that of the magnet and Earth's magnetic field, were of negligible value. The physics concepts used during this experiment were the superposition of magnetic fields and the Biot-Savart law for magnetic dipoles. The first step in the procedure was to compensate the magnetometer for Earth's magnetic field. One does this simply by rotating the magnetometer, in this case my phone, until the x component of the field equals 0. Next, I determine the true position of my phone's magnetometer by sliding my phone over a piece of measuring tape with the magnet oriented along the tape until the x component was at a minimum and the y was at a maximum, and placed a piece of Scotch tape across my phone at this position. I followed a similar procedure after rotating my phone 90 degrees and placed another piece of tape across my phone. Where the two tapes intersect is the true location of my phone's magnetometer. With my phone oriented perpendicularly to the measuring tape and the magnet, I found a distance where the magnitude of the x component was equal to 1,000 microteslas. I then took magnetic field measurements at 1.5, 1.75, and 2 times this distance. Using a linear trend line on a log-log plot of the magnetic field versus the distance, I was able to determine the distance dependence of the bar magnet was 1 over the distance to the power of 2.87, which agrees fairly closely to the theoretical value of 1 over the distance cubed. I then measured the magnitude of the x component at a distance of 7.2 centimeters with the magnet oriented at a 45-degree angle to be 202.4 microteslas. Here's my experimental data. The average distance where the x component equaled 1,000 microteslas was 7.2 centimeters. The measured magnitude at 1.5 times that distance was 324.2 microteslas. At 1.75 times the distance, the magnitude was 203.2 microteslas. And finally, at 2 times that distance, the magnitude was 137.3 microteslas. Plotting these data, I found that the exponent n was equal to negative 2.87, indicating that the distance dependence of the field of a bar magnet is the distance to the power of negative 2.87. This is the code for my computational model. Using the Biot-Savart law for the magnetic field due to a dipole and the built-in dot product function in GlowScript, I developed a function to calculate the magnetic field due to a dipole at a given observation location in lines 13 through 16. I then adjusted the magnitude of the magnetic dipole to match my observed values at a distance of 7.2 centimeters, at which point I was able to call the dipole function to calculate the field of the dipole oriented at a 45-degree angle. My code output illustrates the behavior of the magnetic field using orange arrows on axis, which is in line with the dipole moment, and off axis, which is oppositely directed and half the magnitude. The white arrow shows the magnitude and direction of the magnetic field at a 45-degree orientation. The calculated magnitude of the x component for this orientation was 250 microteslas, indicating that our observed value of 202.4 microteslas agrees with the theoretical value within 1 order of magnitude. The measured distance dependence of the magnetic field is shown again to be proportional to the distance to the power of negative 2.87. which closely agrees with the theoretical value of 1 over the distance cubed. The measured value of the x component of the magnetic field at a 45-degree orientation was 202.4 microteslas, which is in accordance with my computational model. The first follow-up question asks how the results would differ if we had not canceled Earth's magnetic field prior to measuring the magnetic field only due to the bar magnet. Had I not oriented my phone perfectly east to west, the magnetic field of Earth would have superposed on the magnetic field of the bar magnet, and the magnitudes would have been shifted by the value of Earth's field at that particular orientation. This would have also interfered with the distance dependence calculation because Earth's magnetic field would be consistent regardless of how far the magnet was from the magnetometer. The second question asks how the measurements would differ if two magnets were connected end-to-end and the experiment were repeated. In this case, the magnetic dipole would have a larger magnitude, and the distance required to measure 1,000 microteslas would be considerably smaller. However, the distance dependence would remain the same, assuming that all other aspects of the experiment were held constant. Thanks for watching.